synthetic aperture radar is a form of radar that is used to create images of objects, such as landscapes. These images can be either 2 or 3-dimensional representations of the object. SAR uses the motion of the radar antenna over a targeted region to provide finer spatial resolution than is possible with conventional beam scanning. Radars.SAR is typically mounted on a moving platform such as an aircraft or spacecraft, and has its origins in an advanced form of side-looking airborne radar. The distance the SAR device travels over a target in the time taken for the radar pulses to return to the antenna creates the large synthetic antenna aperture. As a rule of thumb, the larger the aperture is, the higher the image resolution will be, regardless of whether the aperture is physical or synthetic. This allows SAR to create high-resolution images with comparatively small physical antennas. To create a SAR image, successive pulses of radio waves are transmitted to illuminate a target scene, and the echo of each pulse is received and recorded. The pulses are transmitted and the echoes received using a single beam-forming antenna with wavelengths of a meter down to several millimeters. As the SAR device on board the aircraft or spacecraft moves, the antenna location relative to the target changes with time. Signal processing of the successive recorded radar echoes allows the combining of the recordings from these multiple antenna positions. This process forms the synthetic antenna aperture, and allows the creation of higher resolution images than would otherwise be possible with a given physical antenna. Current airborne systems provide resolutions of about 10 cm. Ultra-wideband systems provide resolutions of a few millimeters, and experimental terahertz SAR has provided sub-millimeter resolution in the laboratory. SAR images have wide applications in remote sensing and mapping of the surfaces of both the Earth and other planets. SAR can also be implemented as inverse SAR by observing a moving target over a substantial time with a stationary antenna. Typical operation. In a typical SAR application, a single radar antenna is attached to an aircraft or spacecraft so as to radiate a beam whose wave propagation direction has a substantial component perpendicular to the flight path direction. The beam is allowed to be broad in the vertical direction so it will illuminate the terrain from nearly beneath the aircraft out toward the horizon. Resolution in the range dimension of the image is accomplished by creating pulses which define very short time intervals, either by emitting short pulses consisting of a carrier frequency and the necessary sidebands, all within a certain bandwidth, or by using longer chirp pulses, in which frequency varies with time within the bandwidth. The differing times at which echoes return allow points at different distances to be distinguished. The total signal is that from a beam-width-sized patch of the ground. To produce a beam that is narrow in the cross-range direction, diffraction effects require that the antenna be wide in that dimension. Therefore, the distinguishing from each other of co-range points simply by strengths of returns that persist for as long as they are within the beam width is difficult with aircraft-carryable antennas, because the beams can have linear widths only about 2 orders of magnitude smaller than the range. However, if both the amplitude and the phase of returns are recorded, then the portion of that multi-target return that was scattered radially from any smaller scene element can be extracted by phase vector correlation of the total return with the form of the return expected from each such element. Careful design and operation can accomplish resolution of items smaller than a millionth of the range. For example, 30 centimeters at 300 kilometers, or about 1 foot at nearly 200 miles. The process can be thought of as combining the series of spatially distributed observations as if all had been made simultaneously with an antenna. as long as the beam width and focused on the particular point. The synthetic aperture simulated at maximum system range by this process not only is longer than the real antenna, but, in practical applications, it is much longer than the radar aircraft, and tremendously longer than the radar spacecraft. Image resolution of SAR in its range coordinate is mainly proportional to the radio bandwidth of whatever type of pulse is used. In the cross-range coordinate, the similar resolution is mainly proportional to the bandwidth of the Doppler shift of the signal returns within the beamwidth. Since Doppler frequency depends on the angle of the scattering point's direction from the broadside direction, the Doppler bandwidth available within the beamwidth is the same at all ranges. Hence the theoretical spatial resolution limits in both image dimensions remain constant with variation of range. However, in practice, both the errors that accumulate with data collection time and the particular techniques used in post-processing further limit cross-range resolution at long ranges. The conversion of return delay time to geometric range can be very accurate because of the natural constancy of the speed and direction of propagation of electromagnetic waves. However, for an aircraft flying through the never uniform and never quiescent atmosphere, the relating of pulse transmission and reception times to successive geometric positions of the antenna must be accompanied by constant adjusting of the return phases to account for sensed irregularities in the flight path. SARs in spacecraft avoid that atmosphere problem, but still must make corrections for known antenna movements due to rotations of the spacecraft, even those that are reactions to movements of on-board machinery. Locating a SAR in a manned space vehicle may require that the humans carefully remain motionless relative to the vehicle during data collection periods. Although some references to SARs have characterized them as radar telescopes, their actual optical analogy is the microscope, the detail in their images being smaller than the length of the synthetic aperture. In radar engineering terms, while the target area is in the far field of the illuminating antenna, it is in the near field of the simulated one. Returns from scatterers within the range extent of any image are spread over a matching time interval. The interpulse period must be long enough to allow farthest range returns from any pulse to finish arriving before the nearest range ones from the next pulse begin to appear, so that those do not overlap each other in time. On the other hand, the interpulse rate must be fast enough to provide sufficient samples for the desired across-range resolution. When the radar is to be carried by a high-speed vehicle and is to image a large area at fine resolution, those conditions may clash, leading to what has been called SAR's ambiguity problem. The same considerations apply to conventional radars also, but this problem occurs significantly only when resolution is so fine as to be available only through SAR processes. Since the basis of the problem is the information carrying capacity of the single signal input channel provided by one antenna, the only solution is to use additional channels fed by additional antennas. The system then becomes a hybrid of a SAR and a phased array, sometimes being called a vernier array. Combining the series of observations requires significant computational resources, usually using Fourier transform techniques. The high digital computing speed now available allows such processing to be done in near real-time on board SAR aircraft. The result is a map of radar reflectivity, including both amplitude and phase. The amplitude information, when shown in a map-like display, gives information about ground cover in much the same way that a black and white photo does. Variations in processing may also be done in either vehicle-borne stations or ground stations for various purposes, so as to accentuate certain image features for detailed target area analysis. Although the phase information in an image is generally not made available to a human observer of an image display device, it can be preserved numerically, and sometimes allows certain additional features of targets to be recognized. Unfortunately, the phase differences between adjacent image picture elements also produce random interference effects called coherent speckle, which is a sort of graininess with dimensions on the order of the resolution, causing the concept of resolution to take on a subtly different meaning. This effect is the same as is apparent both visually and photographically in laser-illuminated optical scenes. The scale of that random speckle structure is governed by the size of the synthetic aperture in wavelengths, and cannot be finer than the system's resolution. Speckle structure can be subdued at the expense of resolution. Before rapid digital computers were available, the data processing was done using an optical holography technique. The analog radar data were recorded as a holographic interference pattern on photographic film at a scale permitting the film to preserve the signal bandwidths. Then light using, for example, 0.6-micrometer waves passing through the hologram could project a terrain image at a scale recordable on another film at reasonable processor focal distances of around a meter. This worked because both SAR and phased arrays are fundamentally similar to optical holography, but using microwaves instead of light waves. The optical data processes developed for this radar purpose were the first effective analog optical computer systems, and were, in fact, devised before the holographic technique was fully adapted to optical imaging. Because of the different sources of range and across-range signal structures in the radar signals, optical data processes for SAR included not only both spherical and cylindrical lenses but sometimes conical ones. Image appearance. The following considerations apply also to real aperture terrain imaging radars, but are more consequential when resolution in range is matched to a crossbeam resolution that is available only from SAR. The two dimensions of a radar image are range and cross-range. Radar images of limited patches of terrain can resemble oblique photographs, but not ones taken from the location of the radar. This is because the range coordinate in a radar image is perpendicular to the vertical angle coordinate of an oblique photo. The apparent entrance pupil position for viewing such an image is therefore not as if at the radar, but as if at a point from which the viewer's line of sight is perpendicular to the slant range direction connecting radar and target, with slant range increasing from top to bottom of the image. Because slant ranges to level terrain vary in vertical angle, each elevation of such terrain appears as a curved surface, specifically a hyperbolic cosine 1. Verticals at various ranges are perpendiculars to those curves. The viewer's apparent looking directions are parallel to the curve's hypcos axis. Items directly beneath the radar appear as if optically viewed horizontally, and those at far ranges as if optically viewed from directly above. These curvatures are not evident unless large extents of near-range terrain, including steep slant ranges, are being viewed. When viewed as specified above, fine-resolution radar images of small areas can appear most nearly like familiar optical ones, for two reasons. The first reason is easily understood by imagining a flagpole in the scene. The slant range to its upper end is less than that to its base. Therefore, the pole can appear correctly top-end up only when viewed in the above orientation. Secondly, the radar illumination then being downward, shadows are seen in the most familiar overhead lighting direction. Note that the image of the pole's top will overlay that of some terrain point which is on the same slant range arc but at a shorter horizontal range. Images of seen surfaces which faced both the illumination and the apparent eye point will have geometries that resemble those of an optical scene, viewed from the eye point. However, slopes facing the radar will be foreshortened and ones facing away from it will be lengthened from the horizontal dimensions. The former will therefore be brightened and the latter dimmed. Returns from slopes steeper than perpendicular to slant range will be overlaid on those of lower elevation terrain at a nearer ground range, both being visible but intermingled. This is especially the case for vertical surfaces like the walls of buildings. Another viewing inconvenience that arises when a surface is steeper than perpendicular to the slant range is that it is then illuminated on one face, but viewed from the reverse face. Then one sees, for example, the radar-facing wall of a building as if from the inside, while the building's interior and the rear wall have vanished, since they lack illumination, being in the shadow of the front wall and the roof. Some return from the roof may overlay that from the front wall, and both of those may overlay return from terrain in front of the building. The visible building shadow will include those of all illuminated items. Long shadows may exhibit blurred edges due to the illuminating antenna's movement during the time exposure needed to create the image. Surfaces that we usually consider rough will, if that roughness consists of relief less than the radar wavelength, behave as smooth mirrors, showing, beyond such a surface, additional images of items in front of it. Those mirror images will appear within the shadow of the mirroring surface, sometimes filling the entire shadow, thus preventing recognition of the shadow. An important fact that applies to SARs but not to real aperture radars is that the direction of overlay of any scene point is not directly toward the radar, but toward the point of the SAR's current path direction that is nearest to the target point. If the SAR is squinting forward or aft away from the exactly broadside direction, then the illumination direction, and hence the shadow direction, will not be opposite to the overlay direction, but slanted to right or left from it. An image will appear with the correct projection geometry when viewed so that the overlay direction is vertical. The SAR's flight path is above the image, and range increased somewhat downward. Objects in motion within a SAR scene alter the Doppler frequencies of the returns. Such objects therefore appear in the image at locations offset in the across-range direction by amounts proportional to the range direction component of the velocity. Road vehicles may be depicted off the roadway and therefore not recognized as road traffic items. Trains appearing away from their tracks are more easily properly recognized by the length parallel to known trackage as well as by the absence of an equal length of railed signature and of some adjacent terrain, both having been shadowed by the train, while images of moving vessels can be offset from the line of the earlier parts of the wakes. The more recent parts of the wake, which still partake of some of the vessel's motion, appear as curves connecting the vessel image to the relatively quiescent far aft wake. In such identifiable cases, speed and direction of the moving items can be determined from the amounts of their offsets. The along-track component of a target's motion causes some defocus. Random motions such as that of wind-driven tree foliage, vehicles driven over rough terrain, or humans or other animals walking or running generally render those items not focusable, resulting in blurring or even effective invisibility. These considerations, along with the speckle structure due to coherence, take some getting used to in order to correctly interpret SAR images. To assist in that, large collections of significant target signatures have been accumulated by performing many test flights over known terrains and cultural objects.